Today we're going to talk about increasing and decreasing functions. So we'll start with some definitions. A function is increasing if f of x1 is less than f of x2 for x1 less than x2. In other words, you read a graph like you read a book from left to right. And as you're going from left to right, x1 is less than x2. When you're going from left to right, x's are always increasing. If the function values are also getting bigger, that means your function is increasing. A function is decreasing if f of x1 is greater than f of x2 for x1 less than x2. Again, as you read a graph from left to right, your x's are always getting bigger. So x1 is going to be less than x2 as you're going from left to right. But if your y values or your function values are getting smaller, then we say that that's decreasing. And a function is constant if f of x1 equals f of x2 for x1 less than x2. In other words, as you're going from left to right, your x's are increasing, but your y values or your function values are remaining the same. So let's look at this graph right here. Now this arrow right here means it goes in this direction forever. This arrow right here means it goes up in this direction forever. So coming from left to right, coming all the way from negative infinity, what is my graph doing? My graph is increasing until we get to A. Then at A, it turns around and starts decreasing until B. From B, it turns and starts increasing until C. Then it remains constant until D. Then we're decreasing, increasing, decreasing, and then we're increasing forever and ever and ever. So when we talk about where a function is increasing, decreasing, or constant, we're going to list them as intervals. So when we do this, we have our increasing, decreasing, and constant. These are x values. So way down here, when x is negative infinity, my function is increasing all the way up to A. And then from A to B, I'm decreasing. Then from B to C, I'm increasing. Then from C to D, I'm constant. Then decreasing. From D to E. From E to F, I'm increasing. From F to G, I'm decreasing. And then from G all the way until infinity, I'm increasing. So these are all intervals. So I'm basically saying from x equals b to x equals c, my function is going up. From x equals d to x equals e, my function is going down. And from x equals c to x equals d, my function is remaining the same. Here's some more definitions. So f needs to be a function that's defined at c. Then the ordered pair c, f evaluated at c is a relative maximum if f of c is bigger than or equal to f of x for all x in an interval a, b containing c. In other words, what I'm saying here is that the ordered pair c, f evaluated at c is a relative maximum. If you can form a little neighborhood around c, we're coming from the left and coming from the right, that c, f of c is the biggest point. C, f of c is a relative minimum if f of c is less than or equal to f of x for all x in the interval a, b containing c. Again, what that means is if you can form a little neighborhood around c, we're coming from the left and coming from the right, that ordered pair c, f of c is the smallest point. So if we look here, look at A right here. I can form a little neighborhood around A. We're coming from the left and coming from the right. It's the biggest point. So this would be a relative maximum. Here at B, coming from the left and coming from the right, it's the smallest point. So the ordered pair B, f evaluated at B would be a relative minimum. Here we'd have a relative maximum, a relative minimum, a relative maximum, and another relative minimum here. So my relative minimums are going to be the ordered pair B, the function evaluated at B, D, the function evaluated at D, and F, the function evaluated at F. Where my relative maximums are going to be A, the function evaluated at A, C, the function evaluated at C, and E, the function evaluated at E. It's very important that you notice that relative extrema are points. They're ordered pairs, not intervals. Now, I just said relative extrema. What do I mean by that? Well, when you talk about your maximums and your minimums together, we refer to them as extrema. Just like when you talk about your mom and dad together, you typically refer to them as parents. So when I'm talking about maximums and minimums together, they are extrema. Here's another definition. f is a differentiable function defined at c. Then c is a critical value if at the c the derivative is 0 or if at c the derivative is undefined. So let me look back at this graph from this previous slide right here. When the derivative is 0, think back to previous knowledge, that means we have a horizontal tangent. So notice we have a horizontal tangent right here, right here, right here, right here, and right here. And if your derivative is undefined, that means you can't take the derivative or it's not differentiable. And remember from previous knowledge, we talked about that happening at things like corners right here. So you can see we would have a critical value here at A, B, C, D, E, and F, because at each one of those places, the derivative is either 0 or the derivative is undefined. So here I have another little curve for you right here. Relative extrema are going to occur at the critical values, right? We can see that we have a relative maximum here, which would give us that nice horizontal tangent, and we have a relative minimum here, which would also give us that nice horizontal tangent. Where do relative maximums occur? That occurs when your function goes from increasing to decreasing. So your relative maximums are basically like the tops of your mountain, the peak of your mountain. When you get to the peak of the mountain, you were just hiking up, and now that you're there, the only place you can do is go back down, right? Your relative minimums, those are like your bottom of the valley. So you've gone as far down as you can. Now your only choice going left to right is to go up. So your relative minimums occur when your function goes from decreasing to increasing. Now let's relate this to our calculus. Let's look at this graph again here. And now I'm just going to draw a bunch of random tangent lines. There are clearly infinitely many tangent lines to this curve, right? But I'm just going to highlight a handful of them. So if you look at these tangent lines, this nice yellow tangent line and this red tangent line, what do those two tangent lines have in common? Their slopes are positive. What about this blue and green tangent line? What do they have in common? Their slopes are negative. And this pink one, that slope is positive. So notice I'm going from increasing, all my tangent lines have positive slope, to decreasing, all my tangent lines have negative slope, to increasing again, my tangent lines have positive slope. So that's an important thing to notice there. So when your function is increasing, the tangent lines have positive slope. Well, what measures the slope of a tangent line? The derivative. So where your function is increasing, your derivative is positive. Where your function is decreasing, the tangent lines have a negative slope. Again, the derivative measures the slope of the tangent line. So where your function is decreasing, your derivative is going to be negative. So this is actually called the first derivative test. So when your derivative is positive, that tells you that your original function is increasing. And when your derivative is negative, that tells you that your original function is decreasing. So that's a very important thing to note down. So let's apply this now. Here we have a function x squared minus 6x plus 4, and I want to know, without drawing the graph, where is the function increasing, where is it decreasing, and do I have any relative extrema? Do I have a relative minimum? If so, where? Do I have a relative maximum, and if so, where? All right, so what are the important things here? I'm going to break this down into a 5-step process. Well, we said that your function can only change from increasing to decreasing or decreasing to increasing at these relative extrema, which are where the derivative is 0 or undefined. So here I'm increasing. The only way I could possibly switch to decreasing is if I had a relative maximum. And the only way I could go from decreasing to increasing is if I had a relative minimum there. So the most important thing to start is that we need those critical values. I need to know where is it possible for my function to change from increasing to decreasing or decreasing to increasing. Where is my derivative 0 or undefined? So the first thing I'll find my derivative, 2x minus 6. 2x minus 6 is never going to be undefined, so I'll set it equal to 0. Solve for x, and I get x equals 3 as my only critical value. So that's step 1, is to find those critical values. Step 2, I'm going to draw a number line labeling any and all of my critical values. So I'm going to label them in order on this nice number line. It's negative infinity to positive infinity, highlighting the one critical value I have, which is 3. So here, I'm now going to break this up into my intervals that are inside and outside and in between all of my critical values. So looking from left to right, negative infinity, I'm going to stop at this critical value 3, and then starting at 3, I'll go to positive infinity. So my intervals that are outside and in between all my critical values for this case is just negative infinity to 3 and 3 to infinity. So these intervals here are the intervals where our function is either increasing or decreasing. On this entire interval, either my original function is increasing on that entire interval or decreasing on that entire interval. On this interval right here, 3 to infinity, either my entire function is increasing on that interval or decreasing at that interval. Because the only place that my function could change from increasing to decreasing or decreasing to increasing is at the critical value, and the only critical value I have is 3. So in other words, either my function is completely increasing or completely decreasing on this entire interval. Since when my function is increasing, my derivative is positive, and when my function is decreasing, my derivative is negative, then my derivative is either positive on this entire interval or negative on this entire interval. So whatever holds true for one value in that interval will hold true for all values in that interval. So I'm going to choose a test value from each of those intervals to plug into the derivative to determine the sign. Is the derivative positive? Is it negative? So whatever holds true for one value, I can plug in any value in this entire interval. I could plug in 2, 1, 0, negative 72, negative 5,384. You can choose any value in here and plug it into the derivative. Whatever holds true for that one value will hold true for all values. So either your derivative is going to be positive on this entire interval or negative. Same thing for this one. So I just randomly chose 2 and 5. Again, you can choose any value you want. And I'm going to plug those into the derivative. When I plug 2 into the derivative, I get 2 times 2 minus 6, or negative 2. Now this value itself doesn't matter. The number itself doesn't matter. All that matters is the sign of it, which is negative. So whatever holds true for one value in here will hold true for all values in here. So the derivative is negative on this entire interval. Now I'll plug in 5 from this interval. I get 2 times 5 minus 6, which is 4. Again, the 4 itself is not important. Just the sign of that value being positive is what's important. So now I know that my derivative is positive on this entire interval. So that is really all I need to know, because since I know my derivative is negative on this entire interval, that tells me my original function is decreasing on this entire interval. And since I know my derivative is positive on this entire interval, that tells me that my function is increasing on this entire interval. And so now I'm ready for step 5 to answer the question. So here I draw on my number line. I said, okay, my function's negative on this entire interval, and our derivative is negative on this entire interval and positive on this entire interval, which means that my original function is decreasing on this entire interval and increasing on this entire interval. And so now I'm ready to answer my question. I'm increasing from 3 to infinity. I'm decreasing from negative infinity to 3. Now, do I have any relative extrema? Well, relative maximums happen when you go from increasing to decreasing. But I don't go from increasing to decreasing. I go from decreasing to increasing, which means I have a relative minimum at 3. But your relative extrema are ordered pairs, so I would have to label this as 3, my original function evaluated at 3. So going back to my original function, I'll plug in 3 and I get negative 5. As discussed, there's no relative maximum. And now what I'll do is I'll show you what this looks like graphically. And you can see from negative infinity to 3, we are decreasing. From 3 to infinity, we are increasing. And right here at 3, negative 5, we have that relative minimum. Let's take a look at another example. Let's find where negative x cubed plus 3x squared minus 3x plus 10 is increasing, where it's decreasing, and we'll find any relative extrema. So step 1, remember, was to find those critical values. Critical values happen where the derivative is 0 or undefined, so I need to find my derivative, which will be negative 3x squared plus 6x minus 3. That's never going to be undefined, so I'll set it equal to 0, and I will need to factor. Notice these are all divisible by 3, so I'm actually going to pull out a negative 3 to get a nice leading coefficient of a positive 1. Here I can factor this, and that factors into x minus 1 times x minus 1. And so now I'll set the factors equal to 0. Negative 3 is never going to be equal to 0, so we ignore it. And when we set x minus 1 equal to 0, we get 1. And here, where we set x minus 1 equal to 0, we get 1. So again, we only have one critical value, and it's 1. I'll draw my number line labeling that. From here, I can get my intervals, negative infinity up to stop at 1, 1 up to infinity. And we're going to just choose test values from there. I'm just going to pick some x value in here. It doesn't matter. You can pick any x value you want as long as it fits this interval. And some x value in there. So I chose 0 and 2. So into my derivative here, I'm going to plug in 0 and I'm going to plug in 2. Now it's up to you which version of your derivative you want to plug these values in. You can plug them into the unfactored form. Now when you plug in 0, right, negative 3 times 0 squared goes away, 6 times 0 goes away, and we're left with negative 3. That's pretty easy. When you plug in 2, though, you can plug 2 in here and do negative 3 times 2 squared plus 6 times 2 minus 3, or you can plug 2 into the factored form, which might just be a little bit easier. So then negative 3 times 2 minus 1 times 2 minus 1 gives me negative 3 times 1, which is negative 3. So what happened? When I plugged in 0, I got negative 3, which meant my function was decreasing. When I plugged in 2, I got negative 3, which also means my function is decreasing. So my function never actually increases. The only place it can change direction is at those critical values, and we only had the one critical value, which was 1, and my function didn't change. It went from decreasing to decreasing, which is fine. So it's not increasing. It's decreasing from negative infinity to 1 and from 1 to infinity. Now, some of you might be asking, why wouldn't I say it's just decreasing from negative infinity to infinity? And the answer to that is because technically at 1, it's not decreasing. At 1, it's constant, where that derivative is 0. It's like this little plateau that you hit. So when you plug in 1 into the derivative, you get 0, which isn't increasing and it isn't decreasing, right? Because 0 isn't positive and it isn't negative. Now, we don't have any relative minimums because we did not go from decreasing to increasing. And we don't have any relative maximums because we didn't go from increasing to decreasing. So all this function did was went from decreasing to decreasing, and it had no relative extrema. So let's look at what that looks like graphically. Notice I go from decreasing, hit this little plateau right here, where technically at this moment right there, I'm constant, and then I go back down to decreasing. So it is possible that at your critical value, your function does not change directions, and that you don't have a relative extrema. Let's find where g of x equals 2x cubed plus 9x squared minus 60x plus 1 is increasing, where it's decreasing, and find any relative extrema. So we'll go through that 5-step process again. Step 1, we'll find those critical values. So we're going to need to find our derivative. 6x squared plus 18x minus 60. That's never going to be undefined, so I'll set it equal to 0. Notice they're all divisible by 6, so I'm going to go ahead and pull out that common factor of 6. And I have x squared plus 3x minus 10. That factors into x minus 2 times x plus 5. And that gives me a critical value when I set 6 is never going to be equal to 0, so we ignore it. X minus 2 equals 0 gives me 2. X plus 5 equals 0 gives me negative 5. So here I have two critical values, 2 and negative 5. So when I label my number line, I got to label them in order. Negative 5 comes before 2. So now for my intervals, I'm going to go from negative infinity, stop at negative 5. Go from negative 5, stop at 2, and then go from 2 to infinity. And so now I'm going to choose x values from each of those intervals. You can choose any x value you want. Typically, as I said before, picking values like 0, 1, and negative 1 usually help. Those are easier numbers to work with. Here, I'll pick negative 6. Here, I'll pick 0. And here, I'll pick 3. So now I'm going to plug each of those test values into my derivative. Whatever holds true for -6, if my derivative is positive or negative, will hold true for all values in here. Same thing here. Whatever holds true for 0 will hold true for all values here. Whatever holds true for 3 will hold true for all values in there. It is up to you. You can plug these values into the actual derivative, or you can plug it into the factored form. So we're going to plug in -6, 0, and 3. And I'm going to go ahead and plug them into the factored form. But as I said before, the value that you get out isn't important. Just the sign of it is. So when I plug in -6, I have 6 times -6 minus 2 times -6 plus 1. It actually doesn't matter what this number is. All that matters is it positive or negative? So when I have 6 here, that's a positive. -6 minus 2 is a negative, and -6 plus 5 is a negative. So I have a positive times a negative, which is going to give me a positive. Again, the actual number doesn't matter, just its sign does. So you don't even have to calculate it. You just need to know, is it positive or is it negative? And here we saw that it was positive. Whatever holds true for one value will hold true for all values. So the derivative is positive on that entire interval. Plug in 0, same thing. I don't even care what the number is. I have a positive times a negative times a positive. So the derivative is negative on that entire interval. Plug in 3. I have a positive times a positive times a positive, which means my derivative is positive on that entire interval. So to mark that, since we're positive on the entire first interval, my function is increasing. I've got this backwards. I see that now. On this entire interval, my function is decreasing. That should be going down. And on my entire interval here, my function is positive. That should be going up. So I should be increasing. Remember these arrows, that should be going up, this should be going down, and that should be going up. I made a little mistake. But we are increasing from -infinity to -5 and 2 to infinity. I'm decreasing from -5 to 2. Did I switch from increasing to decreasing? I did at -5, so that's where I'm going to have my relative maximum. Did I switch from decreasing to increasing? I did at 2, so that's going to be my relative minimum. So my relative minimum occurs at 2, and then to find the ordered pair, I'll plug 2 into my original function, which gives me -67. For my relative maximum, it happens at -5. So to find the y value, I'll plug -5 into the original function, and I get the ordered pair -5, 276. Let's take a look. I'm increasing, decreasing, increasing, relative maximum, relative minimum. So it did line up. Let's do one more example of finding increasing, decreasing, and relative extrema. Step 1, find those critical values by setting the derivative equal to 0 or determining where it's undefined. The derivative is 4x cubed minus 4x. That's never going to be undefined, so I'll set it equal to 0. Factor out the greatest common factor, which is 4x. And then I'm left with x squared minus 1, which is the difference of two perfect squares. That factors into x plus 1 and x minus 1. Set each of my factors equal to 0, and then I would get 0. I do set this one equal to 0 because it does have an x. 4 times what gives you 0? 0. This will give me 1, and this will give me -1. So I have critical values 0, 1, and -1. So when I draw my number line and I label them, I've got -1, 0, and 1. So my intervals will be -infinity, stop at -1, -1 to 0, 0 to 1, and 1 to infinity. So now I need to choose values from each of those. I'll choose -2, -0.5, 0.5, and 2. And I'm going to plug those back into the derivative to determine, is the derivative positive, in which case my function is increasing, or is my derivative negative, in which case my function is decreasing. I'm going to go ahead and plug these all into the factored form of the derivative. So 4 times -2 will give me a negative. -2 minus 1 will give me a negative. -2 plus 1 will give me another negative. And a negative times a negative times a negative gives me a negative. So my derivative is negative on that entire interval which means my function is decreasing. Plug in negative 0.5. 4 times negative gives me a negative. This is a negative times a positive, which gives me a positive, so my function is increasing on that entire interval. Plug in 0.5, I get a positive times a negative times a positive, which gives me a negative. And plug in 2, I get a positive times a positive times a positive, which gives me a positive. So I go from negative to positive to negative to positive. So my function goes from decreasing to increasing to decreasing to increasing. So negative to positive to negative to positive. So I go from decreasing to increasing, decreasing to increasing. So I can answer the question based on this. My function is increasing. Looks like I copied down the exact same ones from the last time. Interesting that I did that. This should say it is decreasing from negative infinity to negative 1, increasing from negative 1 to 0, decreasing from 0 to 1, and increasing from 1 to infinity. So I'm decreasing from negative infinity to negative 1, increasing from negative 1 to 0, decreasing from 0 to 1, and increasing from 1 to infinity. Do I have any relative extrema? I'm going to have a relative minimum here. I'm going to have a relative maximum here and a relative minimum here. Why? Because I went from decreasing to increasing, that gives me a minimum. I go from increasing to decreasing, that gives me a maximum. And I go from decreasing to increasing, that gives me a minimum. And I've got them labeled on this graph here, decreasing to increasing to decreasing to increasing. So I have a relative minimum at negative 1, 0. I have a relative maximum at 0, 1. And I have a relative minimum at 1, 0. All right, now there's one more thing I want to talk about. We've been talking about relative extrema. In that relative area, it's the biggest point, or in that relative area, it is the smallest point. Well, what about in general on the whole graph? What about absolute biggest and absolute smallest? So we have our absolute extrema. Our absolute extrema is the biggest point on the entire graph and the smallest point on the entire graph. Now, a lot of times when we do our relative extrema, we'll say that C, comma, f of C is an absolute maximum if it's the biggest point on the entire graph. Now, a lot of times we'll actually just cut the graph and we'll say from A to B. So basically we just say, okay, from this point to this point, what is the biggest value and what is the smallest value? So a lot of times we'll cut them off on intervals. All right. So C, comma, f of C is an absolute minimum if it's the absolute smallest point on the entire graph or on the section of the graph that you're looking at. So let's look at this here. We cut this from A to B here, right? So what is the absolute maximum? The absolute maximum is the biggest value on the entire graph, which would be this here. Now this is a relative maximum, but it's not the absolute maximum because there's all these points here that are higher. So this is the absolute largest point on the graph, and the absolute smallest point, notice it's not this relative minimum because all these values are smaller. It happens right here at the end point. So absolute extrema can either happen at relative extrema, which happen at critical values, or at the end points. So absolute extrema can occur at your relative extrema, which happen at critical values, or at the end points, which are given to you. All right, so I break this down into a 3-step process. Let's find the absolute extrema of 3x squared minus 18x plus minus 1 from 1 to 5. So again, what did we say? We said absolute extrema can only happen at the critical values or at the endpoints. Well, the endpoints are given to you, 1 and 5. So step 1 is going to be find the critical values. Remember, that's where the derivative is 0 or undefined. So we'll find the derivative first, 6x minus 18. Set that equal to 0, and we get 3. Now, I only care about the biggest point and the smallest point between 1 and 5. So you need to make sure, does your critical value fit in the interval we're looking at? And in this case, it does. So now I know that my biggest point is either going to happen at 1, 5, or 3. And my smallest point is either going to happen at 1, 5, or 3. So I'm going to plug in the critical values and the endpoints into the original function because I'm looking at where the function has the biggest point and where the function has the smallest point. The only thing I needed my derivative for was to get that critical value. So I'll plug in 1, plug in 3, and plug in 5. And again, I'm plugging it into the original function. So what do you notice? When I plug in 1, I get negative 16. When I plug in 3, I get negative 28. And when I plug in 5, I get negative 16. These are both the biggest point, and this is the smallest point. So now I'm ready to answer my question. My absolute maximum is the biggest I have, and my absolute minimum is the smallest I have. These are ordered pairs. Turns out that I had 2 absolute maximums because negative 16 was the same. So I have 2 absolute maximums at 1, negative 16 and at 5, negative 16. And I have 1 absolute minimum at 3, negative 28. All right, let's look at another example. Let's find the absolute extrema of x to the 4th minus 4x cubed from negative 1 to 1. First thing, find those critical values. The derivative is 4x cubed minus 12x squared. We'll set that equal to 0. Factor out that 4x squared and set the factors equal to 0. That's going to give me 0 and 3. But notice, I'm looking for the absolute maximum and the absolute minimum between negative 1 and 1. 3 doesn't fit, so we throw it away. We just ignore it. And we're just going to look at 0. So when I do step 2, I'm going to plug in negative 1. I'm going to plug in 0, and I'm going to plug in 1. I'm not going to plug in 3 because 3 does not fit in my interval. Now, looking at these values I got out, I get 5, 0, and negative 3. What's the biggest value I got out? 5, so that's my absolute maximum. What's the smallest value I got out? Negative 3, so that's my absolute minimum. And so I can label my absolute max and absolute min accordingly, and those are ordered pairs. Let's do one more example. Let's find the absolute extrema of 4x cubed minus 21x squared plus 18x minus 1 from 0 to 5. Step 1, find those critical values. Take that derivative, 12x squared minus 42x plus 18, and set it equal to 0. Notice they have a 6 in common, and when I pull out a 6, I'm left with 2x squared minus 7x plus 3, which factors into 2x minus 1 and x minus 3. Set my factors equal to 0. 6 is never going to be equal to 0, so ignore it. Here I get 1/2, and here I get 3. So I have the critical value 1/2, which does fit in my interval, and I have the critical value 3, which does fit in my interval. So now I'm going to plug in both critical values and the endpoints. Plug in 0, I get negative 1. Plug in 1/2, I get 13/4, which is 3.25. Plug in 3, I get negative 28. And plug in 5 and I get 64. So the absolute maximum is going to be 64 and the absolute minimum is going to be at negative 28. And so I can label those as ordered pairs. My absolute min is the ordered pair 3, negative 28, and the absolute max is the ordered pair 5, 64. So that is your absolute extrema. For your absolute extrema, you only need the derivative to determine your critical values, and then you're done with it. Then you're plugging everything back into the original function. So that's it for section 10.1, and I'll see you next time for section 10.2.